There is a star in the constellation Orion that you've almost certainly seen with your own eyes. A brilliant orange-red point of light marking the hunter's right shoulder. And there is a real possibility that it no longer exists. That star is Betelgeuse. It has been there every winter, rising in the eastern sky, unmistakable. And right now, scientists around the world are watching it very carefully. Orion is one of the most recognized patterns in the night sky. It appears in ancient records. Every culture with a tradition of stargazing has a name for it. The bright stars marking its belt, its shoulders, its feet. These are reference points humans have used for navigation and calendar keeping for tens of thousands of years. Betelgeuse is one of the brightest of them. It glows orange-red in a sky full of white and blue-white stars. You cannot miss it, but something has been happening to it. The events of the last several years have been unusual enough that astronomers who have spent decades studying this star are now paying closer attention than at any point in recent memory. Not because they are certain something is wrong, because they are not certain something isn't. Betelgeuse is a red supergiant. That classification matters. It is not a stable middle-aged star like our Sun. It is a massive star in the late stages of its life, burning through its remaining fuel reserves, its outer layers swollen to a size that is genuinely difficult to comprehend. If it were placed at the centre of our solar system, its surface would extend past the orbit of Mars. Mercury, Venus, Earth, Mars, all of them would be inside the star. The asteroid belt would sit near its outer edge. It is roughly 700 times the radius of the Sun, and somewhere between 10 and 20 times its mass. It burns tens of thousands of times brighter. By any measure, it is one of the most extreme objects visible to the naked eye from Earth. Stars this massive do not age quietly. They live fast and end violently. Betelgeuse is only about 10 million years old. Our Sun is nearly 5 billion, but Betelgeuse burns through its fuel so rapidly that 10 million years was enough to bring it to this point. A bloated, churning, unstable, red supergiant approaching the final phase of its existence. At some point, it will exhaust its fuel entirely. The core will collapse in a fraction of a second. The resulting explosion will be visible from Earth in full daylight. It will be one of the most dramatic events in the history of human skywatching. Nobody knows when that happens. That uncertainty is not a gap that better instruments will soon close. It is a fundamental limitation of what we can observe. We can study the surface of Betelgeuse. We can analyze its light, track its brightness, map its atmosphere. We cannot see inside it. The core is hidden. And what is happening in that core right now determines everything about how much time this star has left. Here is where the distance problem becomes genuinely unsettling. Betelgeuse is approximately 700 light-years from Earth. That means the light reaching your eyes tonight left the star around the year 1300. The 100 Years' War had not started yet. The Black Death had not reached Europe. Columbus was nearly 2 centuries away from setting sail. That is when the light you're seeing tonight departed Betelgeuse. Whatever the star has done since then, we have not seen it yet. The information is still travelling toward us at the speed of light. If Betelgeuse exploded 500 years ago, we would not know. The light from that explosion would still be on its way. If it exploded last week, we would not know that either. This is not a hypothetical problem. It is the reality of observing objects At cosmic distances, we are always looking into the past. With Betelgeuse, that past is 700 years deep. What we do know is what happened starting in 2019. The star began dimming, not in its usual pattern. It has normal brightness cycles that astronomers track routinely. This was different. It dimmed sharply and dramatically, losing roughly 60% of its visible brightness over a matter of months. Telescopes around the world redirected towards it. The question being asked openly, in journals and in public, was whether this was the beginning of the end, whether Betelgeuse was entering the final phase before a supernova explosion. The answer turned out to be more complicated than a simple yes or no, and the investigation that followed revealed things about this star that nobody had anticipated. A companion star nobody knew existed. Mass ejections of a scale never before observed on any star, other than the Sun. Behaviour in the years after the dimming that has still not fully returned to normal. Scientists are careful about how they communicate all of this. They hedge, they qualify, they note the enormous uncertainties in the models. But something has shifted in the level of attention being paid to Betelgeuse, and that shift reflects a genuine change in what astronomers are seeing. The light reaching your eyes when you look at Betelgeuse tonight left that star somewhere around the year 1300, and whatever has been happening there since then, we have no idea. To understand why scientists are paying such close attention to Betelgeuse right now, you need a sense of what it actually is. The numbers are the kind that genuinely break your brain if you sit with them long enough. Start with size. Betelgeuse has a radius roughly 700 times that of the Sun. That number sounds large, but it doesn't fully land until you think about what it means in concrete terms. If you pulled the Sun out of the centre of our solar system and dropped Betelgeuse in its place, the surface of the star would extend past Mercury, past Venus, past Earth, past Mars. You would be inside the star. The asteroid belt sits at roughly 2.2 to 3.2 astronomical units from the Sun. Betelgeuse's surface would push right up against it. Everything you know about the inner solar system, every planet, every orbit, every place humans have ever lived or visited, would be submerged inside a single star. The mass is between 10 and 20 times that of the Sun, depending on which measurements you use. The uncertainty exists because Betelgeuse is genuinely difficult to measure precisely. Its outer layers are turbulent and irregular. Its distance has been revised multiple times over the past 2 decades. The current best estimate puts it somewhere around 700 light-years from Earth, though even that figure carries a margin of error. What astronomers agree on is the general category. This is a very massive star in the final stages of its life, burning through its remaining fuel at a rate the Sun will never approach. The luminosity figure is staggering. Betelgeuse puts out somewhere between 90,000 and 150,000 times as much energy as the Sun every second. It is genuinely one of the most luminous stars in the galaxy that is visible to the naked eye. The only reason it doesn't dominate the sky the way the Sun does is distance. At 700 light-years, even that extraordinary output is diluted across an enormous expanse of space. What reaches your eyes on a clear night is a fraction of what the star is actually producing. The temperature at Betelgeuse's surface is roughly 3,500 Kelvin, about half that of the Sun. Despite being much cooler, the star's enormous size more than compensates for this lower temperature, making it far more luminous overall. This is what astronomers mean when they classify it as a red supergiant, cooler than blue giants, but vastly larger. The internal core, however, reaches tens of millions of Kelvin as it burns progressively heavier elements. This temperature gradient, cool surface, inferno core, is fundamental to understanding what makes a red supergiant so structurally unstable. The age tells you something important. Betelgeuse is roughly 10 million years old. The Sun is about 4.6 billion years old. There is no comparison. Betelgeuse has lived less than 1/4% of the Sun's current age. It is already dying. Massive stars burn so hot and so fast that they consume their fuel in a cosmological eye blink. The Sun will burn steadily for another 5 billion years or so. Betelgeuse has no such patience. It has been racing through its fuel since the moment it formed. That pace is why it looks the way it does now. What you're looking at when you see Betelgeuse in Orion is a red supergiant. That label tells you exactly where the star is in its life. Stars spend most of their existence on what astronomers call the main sequence, a stable phase where they burn hydrogen in the core and maintain a rough equilibrium between the outward pressure of fusion and the inward pull of gravity. The Sun is a main sequence star. It has been burning hydrogen for nearly 5 billion years. It will keep doing so for billions more. Betelgeuse left the main sequence a long time ago. It exhausted its core hydrogen. It expanded. The outer layers cooled as they spread across an enormous volume, shifting the star's colour from the blue-white of a young massive star toward orange and red. The core, meanwhile, kept collapsing inward and heating up, burning through heavier and heavier elements. This is what a red supergiant is. It is a star in its final act, bloated and brilliant, running out of options. The atmosphere of a red supergiant is nothing like the surface of a stable star. It is not a clean, defined boundary. It is an extended, churning, semi-transparent region where material is constantly rising and falling and being ejected outward into space. Betelgeuse is losing mass continuously. The rate of mass loss is roughly 30 million times higher than the Sun's solar wind. It is, in a meaningful sense, evaporating. The material it sheds forms a vast cloud of gas and dust surrounding the star. That cloud extends for light years in every direction. Inside that atmosphere, convection operates on a scale that has no equivalent in our solar system. The Sun has convection cells, rising columns of hot plasma, but the largest of them are relatively small compared to the star itself. On Betelgeuse, individual convection cells are estimated to be comparable in size to Earth's entire orbit around the Sun. These enormous bubbles of plasma rise from the interior, push against the surface, sometimes break through into the extended atmosphere above. The star's surface, when observed directly through the most powerful telescopes, is not uniform. It is patchy and uneven, showing bright regions and dark regions that shift over time. This is direct evidence of those massive convection cells churning beneath the visible surface. The pulsation cycle adds another layer of complexity. Betelgeuse brightens and dims over a period of roughly 400 days as the star physically expands and contracts. The radius is not fixed. The star breathes in a sense, swelling outward and then contracting back. The changing surface area affects the total light output we observe. This pulsation is driven by the same internal processes that produce the convection. The two effects interact with each other in ways that are not fully understood. There are multiple overlapping cycles at different periods, and disentangling them has occupied astronomers for decades. This is the object sitting in the shoulder of Orion. Not a stable, predictable point of light. A volatile, pulsating, mass-shedding red supergiant with an atmosphere the size of the inner solar system. Convection cells as large as planetary orbits. A core burning through its final fuel reserves. The sun will die quietly, shrinking into a white dwarf after a few billion more years. But Betelgeuse is not going to do anything quietly. In the fall of 2019, astronomers started noticing something wrong with Betelgeuse. It wasn't doing what it was supposed to do. Betelgeuse is a variable star. It brightens and dims on a regular cycle of roughly 400 days, and astronomers had been tracking that cycle for generations. The variations were expected. They were documented. They were part of the star's known behaviour. What started happening in October 2019 was different. The star was dimming faster than the cycle predicted. It was dropping further than it should have, and it wasn't stopping. By November, the numbers were drawing attention. Astronomers who tracked variable stars began flagging the data. Something was off. The dimming continued through December, and by January 2020, it had become impossible to ignore. Betelgeuse had dropped from roughly magnitude 0.5, placing it among the very brightest stars in the sky, to around magnitude 1.7. That is a difference that doesn't sound dramatic until you understand what it means. The star had lost roughly 60% of its visible brightness. Standing outside on a clear night and looking at Orion, you could see it with your own eyes. The shoulder of the hunter had gone noticeably dark. The reaction in the astronomical community was immediate. Telescopes were redirected. Observing time was reallocated. Papers began moving through preprint servers before they'd gone through formal peer review, because researchers wanted the data out fast. The question circulating openly was the one everyone was thinking. Was this it? Was Betelgeuse finally showing the signs that precede a supernova explosion? Nobody said it casually. These are careful people. But the question was there, in print, in discussions, in the language of papers that were unusually direct about the possibility. The public noticed too. Betelgeuse trended on social media. News outlets ran headlines about the dying star. Astronomers who had spent careers working in quiet obscurity were suddenly fielding interview requests. The Great Dimming, as it came to be called, had crossed over from scientific curiosity into something much larger. People were going outside and looking at Orion. Some of them had never done that before. Ground-based observatories around the world pivoted to track the event in detail. Amateur astronomers with backyard equipment contributed observations alongside professional data. The monitoring was relentless and coordinated in ways that only happen when the astronomical community recognizes something truly exceptional is unfolding. Networks of researchers shared preliminary findings within hours. The collaborative urgency reflected a shared understanding that whatever was happening to Betelgeuse, it was rare, it was happening now, and waiting for the formal publication process to unfold could mean missing crucial details. This was science in real time, driven by immediate necessity rather than the usual measured cadence of the field. Meanwhile, the observations kept accumulating, and they were strange. The dimming was not uniform. That was the detail that started shifting the conversation. When astronomers mapped the star's surface using high-resolution imaging, they found that the southern hemisphere of Betelgeuse had darkened far more dramatically than the northern hemisphere. The star wasn't fading evenly across its entire visible disk. Something was happening on one side, something localized. That asymmetry was important. A star preparing to explode would not behave this way. A supernova progenitor going into core collapse would show different signatures entirely. The uneven dimming pointed away from an imminent explosion and towards something else, though nobody was certain what. One early theory focused on the star's temperature. Betelgeuse pulsates, and those pulsations affect surface temperature. A cooling of the photosphere could reduce the star's brightness without requiring any external cause. Some researchers argued the dimming was simply an unusually deep pulsation minimum, the kind of variation that could be explained by the star's known internal processes. The numbers didn't quite fit that explanation either, but it was on the table. Another theory pointed to dust. Red supergiants are known to shed material into the space around them. Betelgeuse does this constantly, losing mass at a rate millions of times higher than the Sun. That shed material can condense into dust in the cooler regions of the star's extended outer atmosphere. Dust absorbs and scatters starlight. If enough of it formed in the right location between us and the star, it could explain a dimming event. The problem was scale. The dimming observed in late 2019 and early 2020 was too large and too sudden to be explained by ordinary dust formation processes. Something unusual had to have driven it. The Hubble Space Telescope settled the question. Observations taken before, during and after the dimming event gave astronomers a detailed record of what had happened to the star's ultraviolet output. Ultraviolet light traces hot, dense material in a star's extended atmosphere. What Hubble showed was striking. In the months before the visible dimming began, the telescope had detected a massive outflow of hot material moving away from the star's southern surface. That material had travelled outward through Betelgeuse's extended atmosphere. As it moved into the cooler outer regions, the temperature dropped, and when the temperature dropped far enough, the material condensed. It formed dust, not a small cloud, a vast one. The dust cloud that formed from this ejected material was large enough to cover roughly a quarter of Betelgeuse's visible surface from Earth's perspective. A quarter of the star blocked. That was the dimming. Not a cooling photosphere, not a deeper than usual pulsation. A colossal eruption from the star's surface had hurled material outward. That material had cooled and solidified into a temporary shield, and the shield had sat between us and part of the star's surface for months. The clarity of this mechanism was striking precisely because it had seemed so elusive just weeks earlier, when the cause of the dimming remained the primary focus of intense scientific debate and speculation. The event had a name before the mechanism was understood. Once the mechanism became clear, it got a second name. Researchers called it a surface mass ejection. It was the largest such event ever directly observed on a star other than the Sun. The ejected mass was estimated at roughly 400 billion times the amount of material a typical solar coronal mass ejection produces. The Sun does something comparable, though on a scale that barely registers against what Betelgeuse managed in 2019. Our star sneezes and satellites flicker. Betelgeuse sneezed and it blocked its own light. After the dimming peaked in February 2020, the star began recovering. Slowly, the dust dispersed. Slowly, the brightness climbed back toward normal levels. By the end of 2020, the star had largely recovered its typical appearance, though careful observation revealed that its southern hemisphere remained subtly different from how it had looked before. The surface hadn't fully healed. The atmosphere in the region of the ejection was still unsettled. Recovery took longer than anyone expected, and in ways that were harder to model than the initial event. The scientific papers that followed over the next 2 years filled in the picture. The eruption had originated in the southern convective zone. The dust cloud had formed between roughly 2 and 5 astronomical units from the star's surface. The photospheric shock that drove the material outward had begun in early 2019, months before the visible dimming started. The whole sequence had unfolded over more than a year, with the dramatic drop in visible brightness representing just one chapter of a longer and more complex event. What the Great Dimming revealed was that Betelgeuse's mass loss is not the smooth, gradual process that earlier models had assumed. The star doesn't quietly exhale material in a steady stellar wind and nothing more. It erupts. It sheds enormous quantities of its own surface in violent, unpredictable bursts. That changes how astronomers think about red supergiants generally, because Betelgeuse is the closest one we have, and what happens there sets the expectations for how the whole class of stars behaves. The textbook picture of red supergiant mass loss had to be revised. The star hadn't dimmed because it was dying, it had dimmed because it had sneezed, and the scale of that sneeze was something nobody had ever seen before. The Sun periodically throws material into space, eruptions called coronal mass ejections that can disrupt satellites and power grids when they hit Earth. And for years, astronomers assumed that red supergiants like Betelgeuse probably did something similar. They were right, but the scale was incomprehensible. A typical solar coronal mass ejection hurls billions of tons of plasma outward at speeds of 1,000,000 miles per hour. It's violent by any human standard. It can knock out power grids across entire continents. It can disable satellites. The 1989 geomagnetic storm, triggered by a solar CME, left 6 million people in Quebec without electricity for 9 hours. That is what a normal stellar outburst looks like from a star like our Sun. What Betelgeuse did in 2019 was approximately 400 billion times larger. Not 400 billion times more energetic in the sense of destroying anything. The distance takes care of that, but 400 billion times more mass. An area of the star's southern surface essentially blew off. Astronomers had a name for it almost immediately: a surface mass ejection. It was the first event of its kind ever directly observed on any star other than the Sun. To understand how it happened, you need to know something about what is going on inside Betelgeuse all the time, even in quiet periods. The star is not stable. It never is. Deep in its interior, enormous columns of hot gas rise toward the surface, cool slightly, and sink back down in a process called convection. Our Sun does this too. The difference is scale. On the Sun, individual convection cells are roughly the size of Texas. On Betelgeuse, a single convection cell can be larger than Earth's entire orbit around the Sun. These are structures so massive that if you placed one inside our solar system, it would swallow everything out to roughly 93 million miles. There are only a handful of these cells churning inside Betelgeuse at any given time, each one a slow churning column of plasma thousands of times larger than any planet. In the months leading up to the Great Dimming, one of these convection cells pushed upward with unusual force. The plasma in that upwelling rose toward the photosphere, the visible surface of the star, and broke through. At almost exactly the same moment, Betelgeuse was expanding outward in its pulsation cycle. The star pulses regularly, contracting and expanding over a period of roughly 400 days. The outward expansion and the rising convective upwelling hit at the same time. The two effects reinforced each other. The result was an enormous bubble of superheated plasma launched outward from the southern hemisphere of the star. Not a gradual outflow, a violent expulsion. That plasma moved outward through Betelgeuse's extended atmosphere at tremendous speed. The star's atmosphere is not a thin shell. It extends outward for an enormous distance, and the material gets cooler the farther it travels from the core. As the ejected plasma moved through these outer layers, the temperature dropped. At a certain point, the temperature was low enough that the material could no longer remain as hot gas. It began to condense. The plasma cooled into dust, and that dust spread across a vast region of space between the star and Earth, formed a cloud dense enough to block roughly a quarter of Betelgeuse's visible surface from our perspective. That was the Great Dimming. A dust cloud, not a dying star. A cosmic sneeze that temporarily draped a dark veil over part of the star's face. From Earth, we saw the star's brightness fall by about 60% over a few months. From the star's perspective, it had simply exhaled more violently than usual. The dust cloud persisted for months before gradually dispersing back into space, a visible reminder that even the most violent stellar events have measurable timescales and observable consequences that can be tracked and studied from our vantage point across the vast distances of space. What made this discovery so significant was not just the explanation itself, it was what the explanation revealed about how Betelgeuse loses mass. Before 2019, the working assumption was that red supergiants shed their outer layers gradually, through a more or less continuous stellar wind. Gas drifts slowly outward. Material accumulates in the surrounding space over long periods of time. It was thought of as a slow, steady process. The surface mass ejection shattered that picture. Betelgeuse doesn't just leak. It erupts. The Hubble Space Telescope observations were essential here. Hubble can observe in ultraviolet wavelengths that ground-based telescopes cannot access through Earth's atmosphere, and ultraviolet light reveals hot gas that is invisible at other wavelengths. What Hubble showed was a dense knot of material moving outward from the southern hemisphere of the star, exactly consistent with a localized ejection rather than a uniform dimming. The southern hemisphere was darker. The northern hemisphere, while variable, did not show the same dramatic drop. Something specific had happened in the south. The mass involved was staggering. Betelgeuse loses material all the time. Its stellar wind alone carries away mass at a rate roughly 30 million times higher than the Sun's solar wind. But in the 2019 event, the star lost roughly twice the normal amount of material from its southern hemisphere over just 3 months. All of that material concentrated into the dust cloud that blocked our view. 2 times the normal mass loss rate. In 3 months, from one hemisphere, it recovered eventually. The dust dispersed. The star's brightness climbed back toward normal over the following year, but the recovery was slow, and it was strange. The southern hemisphere of Betelgeuse showed lingering anomalies well after the dust had cleared. The photosphere in that region appeared to have been physically disrupted by the event. The surface itself had been altered. Researchers tracking the star's behaviour noted that by some measures, Betelgeuse was still not fully back to its pre-2019 baseline years later. The scars of such a violent ejection do not fade quickly, even on stellar timescales, where processes unfold over years and decades rather than human hours and days. This was also the first confirmed observation of a surface mass ejection on any star beyond our own Sun. That distinction matters. It means everything astronomers now think they know about how this process works is based in part on this single event. There is no large sample size. There is no comparison database. There is one star, one event, and a set of observations that scientists are still working to fully interpret. The models that existed before 2019 did not predict a surface mass ejection of this scale. They had to be revised. What the 2019 event suggested, and what subsequent research has continued to reinforce, is that Betelgeuse's mass loss is episodic and violent, rather than smooth and continuous. The star builds up, erupts, settles, and presumably builds up again. The circumstellar shells of material surrounding Betelgeuse, enormous structures stretching light years in every direction, may be the accumulated record of previous events like this one, each shell representing a past eruption that scattered material far into space. The Great Dimming was not unprecedented in Betelgeuse's history. It was just the first one humans were watching closely enough to understand. The Great Dimming hadn't been a warning sign of imminent death. It had been a glimpse of just how violently Betelgeuse sheds its outer layers as it burns through the final fuel reserves of its life. One of the stranger things about Betelgeuse is that, for all the time astronomers have spent studying it, it kept a fairly significant secret for a very long time. After the Great Dimming settled down and researchers began piecing together what had actually happened, they returned to a problem that had been sitting unresolved for years. Betelgeuse dims and brightens on multiple cycles. There is a roughly 420-day pulsation period driven by the star's own internal processes, a well-understood rhythm of expansion and contraction. There are shorter secondary cycles layered on top of that, but there was also a longer, slower variation, a cycle lasting approximately 2.100 days, or just under 6 years, and nobody had a satisfying explanation for it. It didn't fit neatly into any model of internal stellar pulsation. The numbers kept coming up slightly wrong. Researchers had been trying to account for it for decades. Some attributed it to convective patterns deep inside the star. Others proposed complex interactions between different pulsation modes. None of it quite worked. Then in 2024, a group of researchers published something that reframed the entire question. They weren't looking at what was happening inside Betelgeuse. They were looking at what might be orbiting it. The evidence came from 8 years of observations using the Hubble Space Telescope, supplemented by data from ground-based observatories. What the researchers found in that data was a pattern, a recurring disturbance in the gas surrounding Betelgeuse, appearing on a predictable schedule, suggesting that something was passing through the star's extended outer atmosphere, not orbiting at a clean, distant remove the way planets orbit the Sun, actually moving through the diffuse outer layers of gas that surround Betelgeuse for enormous distances beyond its visible surface. Each pass left a detectable trace. The gas was disturbed. The ultraviolet signal changed. There was a wake. Andrea Dupree, an astronomer at the Center for Astrophysics at Harvard and Smithsonian, described it this way. It was like a boat moving through water. The companion was cutting through Betelgeuse's atmosphere and leaving a ripple that Hubble could detect in the data. That analogy understates how strange the situation actually is. The atmosphere Siwarha is moving through is not empty space with a thin scattering of gas. It is the extended outer envelope of one of the largest stars known to exist. The companion isn't grazing the edges of something distant. It is travelling directly through the outer layers of a red supergiant hundreds of times the size of our entire Sun. The companion was given a formal name, Siwarha. It is an Arabic name meaning her bracelet. That fits precisely, since Betelgeuse itself is an Arabic name meaning hand of the giant. A bracelet on the hand of the giant. The naming is poetic, but the discovery behind it is not sentimental. It was the result of years of careful observation and pattern recognition across an enormous data set. What made the discovery genuinely surprising wasn't just that a companion existed, it was what the companion turned out to be. When the initial evidence for Siwarha began accumulating, astronomers had reasonable assumptions about what they were looking for: a companion embedded in a red supergiant's extended atmosphere, on a tight orbit lasting only 6 years, would be subject to enormous gravitational and physical stress. Most researchers expected it to be a compact object, a white dwarf perhaps, the dense remnant of a smaller star that had already completed its life cycle, or possibly a neutron star, something small, dense and old. A dead or dying star dragged close by Betelgeuse's gravity, sweeping through the outer gas on each orbit. That was the working assumption. In October 2025, researchers from Carnegie Mellon University published results that contradicted that assumption entirely. Their observations indicated that Siwarha was not a compact remnant at all. It appeared to be a young star, roughly the size of our Sun, still early in its life, not dead, not dying, young. That was not what anyone predicted. A young Sun-like star sharing a close orbit with an ancient red supergiant approaching the final stages of its life is a deeply unusual configuration. How it formed, how it ended up on that orbit, whether it was always there or whether something brought it closer. These are open questions. The discovery raised more puzzles than it resolved, but it also immediately suggested something important about Betelgeuse's behaviour. If Siwarha is a real companion on a 6-year orbit passing through the star's outer atmosphere, then it is not a passive presence. Every time it makes its pass, it is ploughing through dense expelled material, turbulence disrupting the flow of gas and generating the wake that Hubble detected. That interaction could be contributing to Betelgeuse's long-cycle brightness variation in a straightforward way. The companion physically disturbs the surrounding gas. That disturbance affects how much light we see from the star. There is a more troubling implication as well. Researchers are now actively investigating whether Siwarha's orbital passage had anything to do with the 2019 mass ejection. The timing is not conclusive, but the 6-year orbital period means that Siwarha was making one of its regular passes through Betelgeuse's atmosphere in the same general time frame as the Great Dimming. If the companion's passage through the outer atmosphere created additional turbulence or pressure, it could have reinforced the convective upwelling that triggered the surface mass ejection. It might not have caused the event on its own, but it may have made a large event larger. The models are still being worked through. The researchers are careful about overstating what the current data shows. The connection is plausible. It is not yet proven. What is established is this: Betelgeuse has a companion. That companion is on a roughly 6-year orbit. It passes through the extended outer atmosphere of the star on each orbit, generating a detectable wake. The companion appears to be a young, sun-sized star, which was entirely unexpected, and its presence forces a significant revision in how researchers interpret nearly everything they have observed about Betelgeuse's variability over the decades. Consider what the 8 years of Hubble data actually represent. Astronomers were looking at one of the most studied stars in the sky and still finding something fundamental that had gone undetected. Not because the equipment wasn't good enough in earlier decades, and not because no one was paying attention, but because identifying the signature of a companion embedded in the extended atmosphere of a red supergiant requires precisely the kind of long baseline ultraviolet monitoring that Hubble made possible, analysed with the specific expectation that a periodic signal might indicate orbital motion rather than internal stellar dynamics. The companion wasn't hiding. The tools and the interpretive framework needed to find it simply weren't in place until recently. The name Siwarha was proposed in research published ahead of the formal confirmation, suggested as fitting for an object whose existence had been theorized but not yet directly confirmed. Her bracelet circling the hand of the giant. The Arabic astronomical tradition that named Betelgeuse roughly 1,000 years ago could not have known there was a companion. The name still fits. The discovery also sharpened a question that researchers had not previously needed to ask. If Siwarha is a young star, where did it come from? Stars form from the same cloud of gas and dust, typically at roughly the same time. A young companion orbiting an ancient red supergiant doesn't fit that picture cleanly. One possibility is that Siwarha formed much later from material that Betelgeuse itself expelled during earlier phases of mass loss. Another is that it was captured. Another is that the current estimates of Siwarha's age are imprecise and the situation is more complicated than the preliminary data suggests. None of these explanations is simple. What is clear is that Betelgeuse spent decades being studied intensively and still managed to conceal something this significant. The scientific community's understanding of the star, its variability, its mass loss behaviour, possibly its most dramatic recent event, all had to be revised in light of a companion that no one expected to find, and that turned out to be nothing like what anyone anticipated when they started looking. The star that humanity has watched, named, navigated by for thousands of years, turned out to have company. That discovery changed almost everything scientists thought they understood about why Betelgeuse behaves the way it does. Astronomers had known for decades that Betelgeuse's brightness goes through a long, slow cycle lasting roughly 6 years. For nearly as long, nobody could satisfactorily explain it. The star actually has several distinct cycles running simultaneously. There is a roughly 420-day pulsation cycle that most researchers had accounted for fairly early. That one made sense. Betelgeuse expands and contracts, driven by pressure waves moving through its interior. That expansion and contraction changes how much light reaches us. Shorter cycles of around 185 and 230 days also exist. Those two have plausible explanations tied to the star's internal dynamics. But then there was the long one, approximately 2,100 days, roughly 6 years from peak to peak. That cycle sat in the data for decades and resisted every clean explanation researchers tried to fit to it. The leading theories weren't satisfying. Some researchers proposed it was a different kind of internal pulsation mode, a slower oscillation driven by processes deeper in the star than the 420-day cycle. Others pointed to large-scale convective patterns on the surface, arguing that enormous churning cells might organize and reorganize on roughly that timescale. Neither explanation held up cleanly against the observations. The numbers were close enough to be tantalizing and wrong enough to be frustrating. The 2,100-day cycle was real. It showed up consistently across decades of brightness records, but the mechanism behind it remained genuinely open. Then came Siwarha. Once astronomers confirmed the companion's existence and started working out its orbital parameters, something clicked almost immediately. The orbital period of Siwarha around Betelgeuse comes out to approximately 6 years. That is not a coincidence that requires elaborate statistical argument. The match between the companion's orbit and the mystery brightness cycle was close enough that it essentially answered the question before anyone had to do much more work. The 2,100-day period wasn't coming from inside Betelgeuse at all. It was coming from something orbiting outside it. The mechanism works like this. Betelgeuse is not a clean, hard-edged sphere of hot gas with empty space around it. The star has a vast, extended atmosphere, layers of gas stretching outward far beyond what we'd think of as its visible surface. Siwarha's orbit takes it directly through this material. Every 6 years, as it completes a full revolution, the companion ploughs through the densest inner regions of Betelgeuse's outer atmosphere. That passage disturbs the gas. It creates turbulence. It produces a wake, a trail of compressed and heated material that streams behind the companion as it moves. Andrea Dupree, leading the research team at the Center for Astrophysics at Harvard and Smithsonian, described it as something like a boat moving through water. The companion doesn't have to be large or dramatic to produce a visible effect. It just has to be there, moving through something dense enough to leave a trail. That wake affects how much light reaches us from Betelgeuse. The disturbed gas adds an additional layer of material between the star's surface and our instruments, scattering and absorbing some of the light that would otherwise come through. From Earth, this registers as a slow dimming that builds as the companion approaches its closest pass through the atmosphere, then gradually fades as Siwarha moves on and the gas settles back. The full cycle from one pass to the next takes approximately 6 years, matching the mystery period almost exactly. Confirming this required seeing the wake directly. The research team used ultraviolet observations from the Hubble Space Telescope, accumulated over nearly 8 years of monitoring. Ultraviolet is particularly useful here because hot, disturbed gas emits strongly in those wavelengths. In the Hubble data, the wake appears predictably, showing up shortly after each time Siwarha passes in front of Betelgeuse, exactly where the orbital model predicted it should be. That timing was crucial. A random fluctuation in the star's atmosphere might produce a similar signal once. A companion on a fixed orbit produces it repeatedly, on schedule, in the same part of the observational cycle every time. The data showed the latter. The wake was real, it was periodic, and it matched the orbit. This was a satisfying resolution to a genuinely long-standing puzzle. Decades of speculation about internal pulsation modes and convective timescales. The answer turned out to be something orbiting through the star's outer layers every 6 years. It's the kind of result that makes the field feel clean for a moment. The mystery period had a cause. The cause was testable. The tests confirmed it. But the discovery immediately raised harder questions. If Siwarha is passing through Betelgeuse's extended atmosphere on a regular 6-year schedule, that passage isn't just a passive observation opportunity, it is a physical interaction. The companion is moving through dense gas at significant orbital velocity. That ploughing motion deposits energy into the atmosphere. It creates turbulence in layers that are already unstable. It disrupts material that was already being driven outward by the star's own pulsations and convective upwellings. The obvious question followed directly. Could that periodic disturbance be contributing to Betelgeuse's mass loss? And the more pointed version of the same question. Could Siwarha's orbital passage have played a role in triggering the 2019 surface mass ejection? Nobody has a definitive answer yet. The timing of the 2019 event and the orbital position of Siwarha at that time have been examined carefully. The results are suggestive without being conclusive. The ejection happened during a phase of the orbital cycle when the companion would have been approaching its closest atmospheric passage. Whether that proximity contributed to the conditions that produced the ejection, whether it helped organize the convective upwelling or added energy to the already expanding pulsation that hurled material off the surface, remains an active area of modelling and debate. What is clear is that the relationship between Siwarha and Betelgeuse is not a distant, gravitational-only interaction. The companion is embedded in the star's atmosphere for significant portions of its orbit. That proximity means the two objects are exchanging material, exchanging energy, influencing each other's behaviour in ways that prior models of Betelgeuse simply didn't account for. Every simulation of the star's mass loss, every model of its atmosphere, every prediction about its future behaviour now has to incorporate the presence of something orbiting through its outer layers every 6 years. That is a significant revision to the picture. Betelgeuse was already the most studied red supergiant in the sky, precisely because of its proximity and brightness. Researchers thought they understood its main physical processes reasonably well. The companion changed that assumption. It introduced a periodic external perturbation into a system that had been modelled as essentially self-contained. It did so at exactly the moments when the star's atmosphere is already under stress from its own internal dynamics. The orbit of Siwarha gave scientists a clock. What that clock suggested was that the star's most dramatic recent behaviour might not have been random at all. While the drama of the Great Dimming and the discovery of Siwarha were unfolding, the thing that scientists quietly kept returning to was a more fundamental question about what is happening inside Betelgeuse right now. Not at its surface, not in its atmosphere, inside. The surface events are dramatic. The companion star discovery is genuinely surprising. But both of those things are, in a sense, peripheral to the central fact about Betelgeuse, which is that this star is dying. It is dying in a very specific way. Understanding that process requires going somewhere no telescope can reach. Betelgeuse is burning carbon in its core. That sounds unremarkable until you understand what it means in the context of how massive stars die. Stars like our Sun spend the vast majority of their lives burning hydrogen. It is the simplest fuel, the most abundant, and it lasts billions of years. Betelgeuse burned through its hydrogen long ago. Then it burned helium. The helium phase was shorter. Now it is burning carbon. The carbon phase in a star of Betelgeuse's mass lasts roughly 1,000 years. Not 1 billion years. Not 1 million years. 1,000 years. That is already an extraordinary compression of timescale. But it gets more dramatic from here. When the carbon is exhausted, the core contracts, temperatures rise, and the star begins burning neon. The neon phase lasts perhaps a few years. After neon comes oxygen, burning for months. After oxygen comes silicon, and silicon burning lasts days. Each successive fuel burns hotter, faster, and produces less usable energy than the one before. The star is running down a list of options, and each option on the list is shorter and more desperate than the last. At the end of that list is iron. Iron is the final product of stellar fusion in a massive star, and it is a dead end. Every element up to iron releases energy when fused. That energy is what holds the star up against its own gravity. But fusing iron requires energy rather than releasing it. When the core of a massive star fills with iron, it has nothing left to burn. The energy source that has been fighting gravity for millions of years simply stops. What happens next takes milliseconds. The iron core, which has been accumulating mass, reaches roughly 1.4 times the mass of the Sun. At that point, it collapses, not slowly. The collapse happens at roughly 1/4 of the speed of light. The core goes from the size of Earth to something roughly 20 kilometers across in under a second. The outer layers of the star, still falling inward, hit that newly formed dense core and rebound outward in a shockwave. That shockwave destroys the star. It is a Type II supernova. The energy released in that single event is roughly equivalent to what our Sun will radiate across its entire 10 billion year lifetime. All of it in seconds. This is what Betelgeuse is moving toward. The question is how far along that sequence it actually is. The stakes of answering this question cannot be overstated. If Betelgeuse detonates as a supernova, it will outshine the full moon for weeks. It will be visible in daylight. The light that reaches Earth will carry the imprint of that catastrophic final moment, a snapshot of the violent transformation happening in the star's core. For astronomers, such an event would be unprecedented in the era of modern telescopes and instruments. A nearby supernova has not occurred within recorded history. The last Type II supernova, visible to the naked eye, appeared in 1987, but that occurred in the Large Magellanic Cloud, roughly 160,000 light-years away. Betelgeuse is only 700 light-years distant. It would be a cataclysm of scientific opportunity. Right now, the interior of Betelgeuse is layered like an onion. The outermost layers are hydrogen and helium, the original material of the star, puffed out into the enormous red supergiant envelope. Below that, the material gets progressively heavier and hotter, moving toward the center. There are shells of burning helium, shells of carbon, and at the center, the carbon-burning core itself. As each fuel is exhausted in the core, it gets pushed outward into a shell, while the next heavier element begins burning in the center. The star is essentially running through the periodic table, working from the inside out. Each new layer burns while the ones above it remain. This structure cannot be observed directly. No telescope sees through the outer layers of a star. What astronomers do instead is build models, detailed calculations of how the interior should behave based on physics, compared against observations of the surface, the pulsation patterns, the luminosity, the spectral composition of the outer layers. The models are sophisticated, they are also uncertain. Different assumptions about mixing, mass loss. Rotation produce meaningfully different predictions about where exactly Betelgeuse is in this sequence. That uncertainty matters enormously, and it matters in a specific direction. If Betelgeuse is in the early stages of carbon burning, it has hundreds or thousands of years remaining in this phase alone, before the rapid cascade toward Orion even begins. If it is near the end of carbon burning, the timeline compresses dramatically. Scientists cannot currently determine from the outside which scenario is accurate. What they can observe is the surface and everything beyond it. And what the surface reveals is a star that is losing mass at a staggering rate. Betelgeuse sheds material into space at roughly 10 million times the rate of the Sun. The Sun loses mass too through the solar wind, but the rate is so slow it is almost negligible over billions of years. Betelgeuse does not have billions of years, and it is not being slow about any of this. That mass has to go somewhere, and it has been going somewhere for a very long time. Infrared observations have revealed that Betelgeuse is surrounded by enormous shells of material, gas and dust expelled by the star over at least the past 100,000 years. These shells are not a recent development. They are a record of outbursts, slow winds, mass ejections going back long before any human being ever looked at the night sky. The star has been shedding itself for longer than modern humanity has existed. The outermost of these shells stretches nearly 7.5 light-years from the star. To put that in perspective, the distance from the Sun to the nearest star system, Alpha Centauri, is roughly 4.2 light-years. The debris field surrounding Betelgeuse is larger than that gap. It is an enormous halo of expelled material, ghostly and diffuse, invisible to the naked eye, but detectable in infrared wavelengths, spreading outward in all directions from a star that is still very much alive at the center. Closer in, there are denser shells, evidence of past episodes where mass loss accelerated, where something in the star's behavior sent larger quantities of material outward. These denser regions are embedded within the broader circumstellar environment, layered records of a turbulent history. The 2019 surface mass ejection added to that record. It was not the first major outburst, it was just the first one humans were able to watch in detail. The sheer scale of the circumstellar environment tells scientists something important. This star has been violent for a long time. The atmosphere is not a stable shell around a calm interior. It is the outer edge of a churning, unstable system that has been shedding material and erupting for thousands of years, driven by convection cells larger than Earth's orbit, pulsation cycles measured in months. Now a companion star ploughing through the outer gas on a 6-year orbit. Everything visible around Betelgeuse, every shell of expelled material, every cloud of dust, every detection of outflowing gas represents something the star has already lost. Mass that will never return. The star at the centre is slightly smaller, slightly lighter than it was when each of those shells was formed, and a star of Betelgeuse's type cannot afford indefinite mass loss. The more it sheds from the outside, the more the interior structure shifts. The more gravity squeezes the core, the faster the burning proceeds. The star is surrounded by the debris of everything it has already lost. Shells of expelled material stretching nearly 8 light years in every direction, monuments to a history of violence that is not over yet. The question that follows every conversation about Betelgeuse, the one that gets asked at every public lecture and in every comment section, is the obvious one. When does it explode? The honest answer is complicated. There is a mainstream scientific consensus. It puts the supernova somewhere around 100,000 years from now. That estimate comes from multiple lines of evidence: the star's mass, its rotation rate, the cluster of stars it was born alongside, and the chemical composition visible at its surface. Feed those numbers into stellar evolution models, and you get a timeline that stretches well beyond anything a human civilization could reasonably care about. 100,000 years. That is longer than our species has existed in its current form, but then came 2023. A paper published that year looked at the problem from a different angle. Rather than using surface properties and mass estimates, the researchers tried to model where Betelgeuse actually sits within its carbon burning phase. Carbon burning is one of the final stages of fusion before a massive star runs out of options. For a star of Betelgeuse's mass, the carbon burning phase lasts roughly 1,000 years total. The question is where in that 1,000 years Betelgeuse currently sits. If it's near the beginning, you have centuries ahead. If it's near the end, the timeline compresses dramatically. The paper concluded that the timeline might not be hundreds of thousands of years. It might be tens of years, not tens of thousands, tens. That number circulated through the astronomical community and landed like a stone. The researchers were careful. They hedged appropriately. They noted explicitly that the models were uncertain, that the carbon burning phase could still have a long time remaining. But the possibility was there, stated in a peer-reviewed paper, that Betelgeuse could go supernova within a human lifetime. Possibly within the lifetime of people already alive right now. The reason the uncertainty is so enormous comes down to a fundamental problem. We cannot see inside the star. Everything we know about Betelgeuse's interior is inferred. We observe the surface, we observe the atmosphere. We can study the circumstellar shells of material the star has already ejected. But the core, where the actual fusion is happening, where the countdown is running, is completely hidden from us. We are standing outside a building trying to figure out what floor the fire is on by watching smoke come out of the windows. The inferences come from multiple sources. Pulsation patterns tell us something about the star's internal structure, the way seismic waves tell geologists about Earth's interior. Luminosity tells us how much energy the core is generating. Surface composition gives clues about what the outer layers contain. And stellar models, built from the physics of nuclear burning and gravity and radiation pressure, tell us what a star of this type should look like at various stages of its life. The problem is that the models disagree with each other. Different assumptions about mass loss rates, about convection, about rotation, produce wildly different results. You can run the same basic star through different models and get timelines that vary by orders of magnitude. Some models assume Betelgeuse is younger and still has considerable time before collapse. Others suggest it is older and closer to the end. The disagreements stem from genuine scientific uncertainty about how red supergiants behave, how much mass they shed into space over time, and how that mass loss affects the internal structure and burning rates. These are not trivial questions. They get to the heart of how stars age and die, and we simply do not have enough observational data from other red supergiants in their final phases to decisively choose between competing approaches. This is not a failure of science. It's an honest reflection of how hard the problem is. We have never watched a red supergiant explode from close range. The last naked-eye supernova visible from Earth was in 1987, in the Large Magellanic Cloud. That event taught us an enormous amount and also revealed that our pre-existing models were wrong in several important ways. The star that exploded in 1987 was a blue supergiant, not a red one. Nobody predicted that. The models said it should have been a red supergiant. It wasn't. That kind of surprise is a reminder of the limits of what we know. That explosion, which we could study in unprecedented detail thanks to modern instrumentation, showed us that stellar explosions contain physics we had not fully accounted for. The explosion was asymmetrical in ways the models had not predicted. Certain elements were distributed differently than expected. These revelations suggested that our understanding of how massive stars end their lives still has significant gaps. There is also a more unsettling layer to this problem. Betelgeuse is roughly 700 light-years away. The light reaching our telescopes tonight left that star around the year 1300. We are not observing Betelgeuse as it is. We are observing Betelgeuse as it was 7 centuries ago. Every measurement, every data point, every model, all of it is built on information that is 700 years old by the time it arrives. This temporal distance creates a peculiar kind of blindness. We can measure the star's brightness, its colour, its pulsations, the way its atmosphere moves. But all of those measurements describe a star that has long since evolved beyond what we are seeing. Internal processes that might have drastically altered the star's destiny have already occurred, unseen by human eyes, hundreds of years before the evidence of them reaches Earth. That means the star could have already exploded. it could have gone supernova during the Black Death, and we would have no way of knowing yet. The shockwave of light from the explosion could be travelling toward us right now, centuries into its journey, still centuries away from arrival. Betelgeuse might not exist anymore. The star we are studying so carefully, building models around, arguing about in papers, might already be a cooling cloud of debris surrounding a neutron star or a black hole. We are, in a very real sense, studying a ghost. This is not a rhetorical flourish. It is the actual physics of the situation. The finite speed of light creates a delay that no technology can eliminate. We cannot call ahead. We cannot send a probe to check. We observe what the universe shows us, and what it shows us is always the past. What we do have is an early warning system. It doesn't beat the light travel delay entirely, but it provides something. When a massive star collapses and explodes, the first thing it releases in enormous quantities is neutrinos. These nearly massless particles interact with matter so weakly that they pass through the entire star almost instantly, even as the explosion is still developing. They travel outward at close to the speed of light, ahead of the visible blast. The light from the explosion takes hours longer to escape the collapsing stellar material. That gap, hours to days, is enough to trigger alerts. Detectors like Supergiant in Japan are watching for exactly this. Supergiant is a tank containing 50,000 tons of ultra-pure water buried deep underground to shield it from background radiation. When neutrinos pass through it, a small fraction interacts with the water molecules and produce faint flashes of light. Under normal circumstances, detecting a handful of these interactions per day is considered successful. If Betelgeuse goes supernova, Supergiant would detect thousands of interactions within seconds. It would be unmistakable. The system would fire an alert to observatories worldwide within minutes. Telescopes would swing toward Orion and begin recording before the visible light even arrived. That warning is in place right now. The detectors are running. The alert protocols exist. The astronomical community has genuinely prepared for this. But none of that resolves the core question of timing. The warning system tells us hours before the visible explosion. It tells us nothing about whether that moment is 50 years away or 50,000. For that, we are still dependent on models that disagree, built on observations of a surface that hides its interior, of a star we are watching 700 years in the past. Some researchers looking at the behaviour since 2019 have noted that Betelgeuse has been acting in ways the standard models didn't predict. The Great Dimming was not in anyone's timeline. The surface mass ejection was unprecedented. The recovery was slower than expected. The companion star's influence is still being modelled. Each of these surprises chips away slightly at confidence in the longer timelines. Not enough to say the shorter timeline is right, but enough to make the question feel genuinely open. The honest answer is that we don't know, and that uncertainty, the gap between what we can observe at the surface and what is actually happening 700 light years away in the hidden core of a dying star, is precisely what makes Betelgeuse so maddening and so fascinating to the people who study it. Whatever uncertainty surrounds the timing, there is considerably less uncertainty about what will happen when Betelgeuse actually goes. The first thing to understand is the scale of what a supernova actually produces. A typical supernova outshines an entire galaxy for a period of weeks, a galaxy containing hundreds of billions of stars. Betelgeuse is roughly 700 light-years away, which is close in astronomical terms. The combination of that proximity and that raw energy output means the event will be unlike anything recorded in human history. Current estimates put the peak brightness somewhere near half-moon levels. That is not a metaphor. You will be able to see it in full daylight, a blazing point of light in the daytime sky. Brighter than Venus, brighter than Jupiter, brighter than anything in the sky, except the sun and the moon. It will be visible during the day for weeks, possibly months, and at night it will cast Artus. The night sky transformation alone is difficult to fully picture. Right now, Betelgeuse sits comfortably among the brightest stars visible from Earth. After the explosion, it will be something categorically different. People will look up and wonder what they're seeing. There will be no context for it. No one alive has ever seen anything like it, and neither did their grandparents or great-grandparents. The last supernova, visible to the naked eye, occurred in 1604. That was before the invention of the telescope. The last one modern instruments actually recorded was in 1987 in the Large Magellanic Cloud, a companion galaxy to the Milky Way sitting roughly 170,000 light-years away. It reached a peak magnitude of about 2.9, visible from the southern hemisphere, but faint. Not remotely comparable. Betelgeuse is closer, much closer, and the star itself is far more massive. The visibility will persist long after the initial peak fades. The fireball will gradually dim over months, but the expanding cloud of ejected material, the nebula forming in real time, will remain visible to the naked eye for years. It will stop being a point of light. The shockwave will push outward at thousands of kilometers per second, sweeping up surrounding gas, lighting it up, spreading across a region of sky that grows visibly larger over time. Eventually, it will resemble what we see today in remnants like the Crab Nebula, the leftover of a supernova observed by Chinese astronomers in 1054. That remnant spans roughly 11 light-years now and is still expanding. Betelgeuse will leave something similar in Orion's shoulder, permanent, changing the constellation for every generation that follows. Now, the reasonable question is whether any of this is dangerous. It is not. The answer here is simple physics. Energy from an explosion spreads outward in all directions equally, covering an ever-expanding sphere of space. Double the distance and the energy per unit area drops to 1/4. The inverse square law. At 700 light-years, the radiation reaching Earth from a Betelgeuse supernova is negligible by the time it gets here. Studies have established that a supernova would need to be within roughly 160 light-years of Earth to cause meaningful harm to life on the surface. Betelgeuse is more than 4 times that distance. The gamma rays, the X-rays, the neutrinos, all of it spreads across such an enormous volume of space that what reaches Earth is, from a biological standpoint, essentially nothing. What we get is the light show, that is all, and the light show will be extraordinary. What scientists will actually learn from the event is where things get genuinely remarkable. The explosion will not arrive without warning. Neutrinos are produced in enormous quantities during a core collapse. They interact so weakly with ordinary matter that they travel through the star itself almost unimpeded, escaping hours before the visible explosion breaks through the outer layers. Detectors like Supergiant in Japan are watching for exactly this signal. When the neutrino burst arrives, it will give astronomers somewhere between a few hours and a day or more of warning before the light from the explosion becomes visible. That window is invaluable. Every observatory on Earth and in space can slew toward Orion and begin recording from the very first moment light escapes the dying star. The shock breakout, the instant the shockwave punches through the stellar surface and becomes visible for the first time, is one of the most scientifically valuable phenomena in astrophysics. It has only been captured a handful of times, never from a star this close, never with the instrumentation available today. After the shock breakout comes the light curve. The brightness will rise, peak, then decline along a trajectory that encodes enormous amounts of information about the star's internal structure, its mass, the distribution of elements in its outer layers. Spectral analysis of the ejected material will reveal what Betelgeuse was actually made of at the time of explosion, the composition of each shell as the shockwave peels them back and sends them outward. Carbon, oxygen, neon, silicon. The heavier elements created in the final stages of burning. The scientists who have spent careers building models of Betelgeuse's interior will finally have direct observational data to test those models against. The explosion is essentially a controlled demolition that exposes everything previously hidden. There is genuine excitement in the astrophysics community about this prospect, and that excitement is not casual. It is the kind that comes from knowing that a once-in-a-civilization scientific event may be approaching. The 1987 supernova, despite being far more distant and far fainter, transformed our understanding of how massive stars die. It confirmed that neutrinos are produced during core collapse. It showed that stellar models were broadly correct but needed revision in specific ways. Betelgeuse will do the same, but with instrumentation that 1987 researchers could not have imagined. From a star close enough that the detail available will be orders of magnitude richer. Researchers have published plans. Telescope committees have reserved contingency time. Trigger systems have been designed specifically for this moment. The scientific preparation has been underway for years. The equipment waiting for this event spans the full electromagnetic spectrum. Radio telescopes, infrared observatories, X-ray satellites, gamma-ray detectors, neutrino tanks buried underground. Each wavelength reveals different physics happening at different stages of the explosion. The complete picture requires all of them operating simultaneously from the earliest possible moment. Missing the initial phases would be like arriving at a crime scene after the evidence has been disturbed. The preparation exists precisely so that nothing is missed. The last naked-eye supernova before 1987 that left a surviving remnant was Tycho's supernova in 1572. Tycho Brahe observed it and wrote about it. It challenged the Aristotelian belief that the stars were fixed and unchanging. Betelgeuse going supernova will not challenge any fundamental beliefs about the universe. This was because we understand what is happening now in ways Tycho Brahe could not. But the scientific return will be immense, and the human experience of watching a new star ignite in a familiar constellation, visible at noon, casting shadows at midnight. Visible for months and years will be something that no one living today has ever experienced, and no one will ever forget. Every major telescope on Earth and in orbit has a plan for the moment Betelgeuse explodes. Trigger files sitting in computers, ready to execute automatically the instant the neutrino detectors fire. Here is what is difficult to communicate about the current state of Betelgeuse research, and it comes down to the difference between what scientists say in papers and what they say to each other. In papers, scientists are careful. They hedge. They qualify every claim with error bars and alternative explanations. They use phrases like broadly consistent with and does not preclude, and further observations are warranted. That is how science is supposed to work. A single unusual event does not prove anything. One strange data point gets filed away. Two strange data points become a footnote. But when the unusual events start stacking up, when the anomalies keep arriving faster than the explanations, something shifts. The language in the papers stays measured. The conversations in the hallways do not. That shift has been happening with Betelgeuse since 2019. It did not start as panic. It started as surprise. The great dimming was genuinely unexpected. Not unexpected in the sense that nobody imagined Betelgeuse could behave dramatically. Everyone knew it was a volatile star. Unexpected in the sense that the specific mechanism, a surface mass ejection on that scale, had never been observed on any star before. Astronomers had assumed red supergiants probably lost mass through something like solar wind processes, steady and gradual. What Betelgeuse did in 2019 was not gradual. It blew off a chunk of its own surface. That had never been seen. Ever. The initial scientific response was cautious optimism. We observed something new. We figured out what it was. The dust cloud explained the dimming. The convection cell and pulsation cycle explained the ejection. The mystery was solved. Science worked. And then the star kept behaving strangely. The southern hemisphere of Betelgeuse, the region where the mass ejection originated, did not recover normally. Months after the dimming ended and the star returned to something approaching its previous brightness, the southern hemisphere was still showing anomalies. The photosphere in that region was disrupted. The temperature patterns were off. The surface was not behaving the way models predicted it should behave after an event like this. 1 year passed, then 2. The anomalies persisted. That was not expected. The models said the star's surface should have settled back into its normal convective patterns within months. It did not. Researchers published papers noting the slow recovery. Those papers were careful. They described the observations. They proposed possible explanations. They noted that the models needed refinement. What the papers did not say, because papers do not say things like this, was that nobody quite understood why the star was taking so long to return to normal, and that the fact that nobody understood it was itself worrying. Then came the companion star. The discovery of Siwarha changed the picture significantly, not just because a companion star was found, but because of what that companion's presence implied. Siwarha orbits through Betelgeuse's extended outer atmosphere every 6 years. That orbit brings it into direct contact with the dense gas surrounding the star. Astronomers began running models to understand what that interaction actually does to Betelgeuse. Some of those models produced uncomfortable results. the orbital timing of Siwarha's last close passage before 2019 aligned with the period leading up to the Great Dimming. It is not proven that the companion triggered the mass ejection. Researchers are very clear about that. The connection is suggestive, not established. But the models that include the companion's gravitational and atmospheric influence show that the periodic orbital passes could be generating enhanced mass loss events. They could be destabilizing the outer layers of the star in ways that make large ejections more likely. If that is true, the 2019 event was not a random outburst. It was, at least in part, a predictable consequence of a system that has been doing this repeatedly for millions of years. And Siwarha will make another close pass. The 6-year cycle continues. Alongside all of this, there are the modelling papers about the core. The mainstream consensus puts Betelgeuse's supernova hundreds of thousands of years in the future. That consensus is based on solid, well-established methods. It accounts for mass, rotation, composition, and comparison with similar stars. Most astronomers stand behind it, but a 2023 paper took a different approach. Modelling the specific phase of carbon burning the star appears to be in based on observed pulsation patterns and luminosity. That paper's conclusion was not hundreds of thousands of years. It was tens of years. The researchers themselves acknowledged the enormous uncertainty in their model. They were not claiming certainty, but the result was serious enough to publish, and serious enough that other researchers took notice. The response to that paper in the scientific community was instructive. It was not dismissed. It was not embraced. It was treated the way scientists treat genuinely uncomfortable results, with careful scrutiny, requests for independent verification, and an acknowledgement that if the assumptions hold, the implications are significant. Several researchers who study stellar evolution noted publicly that the methodology was reasonable even if the conclusion was startling. Nobody said the paper was wrong. Nobody said it was right. The uncertainty simply grew larger. Here is what that accumulation actually looks like from inside the research community. You have a star that performed an unprecedented mass ejection. Its surface took years longer to recover than it should have. A companion star was found that may be periodically destabilizing its outer layers. The 6-year brightness cycle that Companion explains is ongoing, which means more orbital passes are coming. And modelling of the core suggests, with admitted uncertainty, that the timeline to explosion may be dramatically shorter than the standard estimate. Each of these things, taken alone, would be interesting but not alarming. Taken together, they represent something different. They represent a star that is not behaving according to the textbook in multiple independent ways simultaneously. Scientists do not panic. That is not how scientists operate. But there is a particular quality of attention that emerges when researchers believe they may be watching something that will not happen again in their lifetimes, or possibly in human history. Telescope time gets requested more urgently, papers get submitted faster, emails between researchers get longer and more frequent. The Betelgeuse monitoring programs that existed before 2019 were substantial. After 2019, they expanded. After the companion discovery, they expanded again. Andrea Dupre, whose research at the Harvard-Smithsonian Center for Astrophysics has been central to much of what we now know about Betelgeuse's recent behavior, has said publicly that the events since 2019 have been genuinely surprising in ways that matter scientifically. That is careful language. But coming from someone who has spent years watching this star, it carries weight. Surprising in ways that matter is not the language of a researcher who is watching a stable, well-understood object proceed normally through a well-characterized phase of its life. The honest summary is this: Betelgeuse may be exactly what the mainstream models say it is, a red supergiant in the late stages of its life, still with a very long way to go before the final collapse. That is still the most probable assessment, but the probability that something unusual is happening, that the events of the last several years represent a genuine escalation rather than random fluctuation, has been rising. The researchers who are closest to the data are not making dramatic public predictions. They are doing something more telling. They are watching more carefully than ever before. They are publishing more frequently. They are building better models and running them with more urgency. They are keeping the neutrino detectors running and the trigger files current. The instruments are running, the detectors are armed, and the researchers who have spent their careers on this star are watching with the particular kind of attention that comes from not quite knowing whether they are studying a stable object or counting down to the most spectacular event in recorded astronomical history. After the light fades, after the daytime spectacle ends, and the years-long glow dims below naked eye visibility, Betelgeuse will have left something behind. The core is the first thing to consider. When a star of this mass collapses, the outer layers are blasted outward. But the center does not simply vanish, it compresses. In a fraction of a second, the iron core, roughly the size of Earth, is crushed down to an object about 20 kilometers across. That object contains more mass than our entire Sun. It is a neutron star, one of the most extreme physical environments in the known universe, dense enough that a teaspoon of its material would weigh roughly 1 billion tons. Whether Betelgeuse leaves a neutron star or collapses further into a black hole depends on the final mass of that core. Astronomers are not certain which outcome is more likely. The mass estimates for Betelgeuse span a range wide enough that both outcomes remain genuinely possible. The outer layers are a different story. They are not compressed, they are destroyed. The explosion hurls them outward at thousands of kilometers per second, seeding the surrounding interstellar medium with everything Betelgeuse spent 10 million years manufacturing inside itself: carbon, oxygen, silicon, iron. And in the final seconds of the explosion, when temperatures and pressures spike to levels that cannot be sustained, elements heavier than iron are forged in quantities that no other process in the universe can produce efficiently. Gold, platinum, uranium. These elements are created in the collapse itself, scattered into space as the shockwave tears the star apart. The sheer volume of material ejected in a supernova of this magnitude is almost incomprehensible. Betelgeuse will shed a significant fraction of its entire mass, possibly several times the mass of our Sun, in the span of hours. This material expands outward in a shell moving faster than any spacecraft humanity has ever built, fast enough to cross the distance between Earth and the Sun in a matter of days. The energy released in this process exceeds the total energy output of our Sun over its entire 10 billion year lifetime, released in a span of seconds. It is the most violent event that can occur in the universe, short of a collision between black holes or neutron stars. That material does not disappear. It expands outward into the interstellar medium, mixing with the gas and dust already there. Over hundreds of thousands of years, it cools, slows, and gradually becomes part of the raw material of the galaxy. Eventually, somewhere, a region of that enriched medium will collapse under its own gravity. A new star will form, and around that star, if the conditions are right, planets will form from the same material, including the heavy elements that Betelgeuse contributed in its final moments. This is how the universe builds complexity. Stars are not merely light sources, they are factories. They take simple hydrogen and helium, and over millions of years, convert it into almost everything on the periodic table. Then they distribute that material back into SP, ACE when they die. The nebula itself will be visible for a long time. The expanding shell of ejected material will glow for thousands of years as the radiation from the hot remnant energizes the surrounding gas. Over centuries, it will spread across an area of sky that grows steadily wider. Astronomers in the far future, if there are any, will watch it gradually dissipate, its edges blurring into the background of the galaxy. Eventually, it will be gone entirely, absorbed into the interstellar medium. Nothing will mark the spot except, possibly, a faint neutron star spinning in the dark. Orion will look different. This is worth sitting with for a moment. The constellation that humans have used for navigation, mythology, agriculture, and storytelling for tens of thousands of years will change permanently. Every culture that developed under skies where Orion is visible has incorporated it into their traditions. The Egyptians built monuments aligned to it. Arab astronomers named its stars, including Betelgeuse itself. Indigenous peoples on multiple continents mapped their calendars to it. Hunters, sailors, farmers, for all of recorded history, that bright orange-red star in the shoulder has been a fixed reference point. It will not be fixed forever. After the explosion, after the nebula fades over the following centuries, that particular light will be gone. The familiar rice, T-shoulder of the hunter will be empty, a pattern that predates writing, predates agriculture, predates civilization as we understand it, will be permanently altered. What replaces it depends on what the explosion leaves behind. A neutron star at 700 light-years might be detectable with telescopes, but it would not be visible to the naked eye, not even close. The brilliant orange-red point that guided travellers and inspired mythology for millennia would be replaced by darkness. A black hole would be invisible by definition. Either way, the shoulder of Orion will go dark. This is not a tragedy in any meaningful astronomical sense. Stars form, burn, explode, and their material feeds the next generation. Betelgeuse is simply further along in that cycle than our Sun. Its death will be more dramatic, but the principle is the same. The material it returns to space will eventually become something else. New stars, possibly new planets, possibly somewhere the raw ingredients for something living. The connection is direct and not metaphorical. The iron in human blood, the calcium in bones, the oxygen in every breath, none of it was made in the Big Bang. The Big Bang produced hydrogen, helium, and trace amounts of lithium. Everything heavier was made in stars. The carbon that forms the backbone of every organic molecule on Earth came from a star that exploded before our solar system existed. The oxygen came from another. The iron came from yet another. We are, in the most literal physical sense, made of material that was once inside dying stars. Betelgeuse is doing what those stars did. It is building heavy elements in its interior. When it explodes, those elements will be released. The universe will be chemically richer for it. Some small fraction of what Betelgeuse distributes may, over billions of years, find its way into something alive. The oxygen filling your lungs right now came from stars that did exactly what Betelgeuse is preparing to do. And when it finally goes, it will be making the same gift to solar systems that won't exist for another billion years. There is something specific that happens when you look at Betelgeuse after spending real time understanding what it is and what it is going through. It stops being a point of light. It becomes a thing with a history, a thing with an interior, a thing that is, by any reasonable measure, already dying. That shift in perception is hard to undo. Humans have been looking at that star for a very long time. It appears in Mesopotamian astronomical records going back thousands of years. Arab astronomers gave it its name. Cultures on every continent where Orion rises above the horizon built stories around it. It marked seasons. It guided navigation. It told farmers when to plant. For all of that history, across every civilization that ever looked up at it, Betelgeuse was simply there, constant, reliable, part of the furniture of the sky. It never exploded, it never disappeared. Generation after generation looked at the same orange-red point of light in the hunter's shoulder and found it exactly where they left it. That permanence was an illusion, of course. It was always burning through its fuel. It was always moving toward the same end. But the timescales involved are so vast that no human civilization ever had reason to notice. 10 million years is the approximate age of Betelgeuse. Modern Homo sapiens have existed for perhaps 300,000 years. Agriculture is about 12,000 years old. Written records go back maybe 5,000 years. The entire span of recorded human history represents less than 0.1% of Betelgeuse's life. We arrived very late, and yet we arrived in time to watch this particular moment, the great dimming, the surface mass ejection, the discovery of Siwarha, the modelling papers suggesting the core burning timescales might compress the timeline dramatically. The lingering atmospheric anomalies that scientists are still trying to explain. All of it happening within the last 6 years. That is either a coincidence or it isn't. Scientists are careful about that distinction. Most of them will not say definitively that these events are connected to an imminent end, but they are watching with a specific kind of attention. The uncertainty is genuinely uncomfortable. Not the ordinary scientific uncertainty, where the answer is unknown, but the range of possibilities is bounded and sensible. This is a different kind. The honest range stretches from tens of years to hundreds of thousands of years. Those are not refinements of each other. They are completely different futures. One of them puts the explosion within living memory. One of them puts it long after every language currently spoken on Earth has gone extinct. The models cannot choose between them because we cannot see inside the star. The core is hidden. Everything we know about it is inferred. And there is the light travel problem sitting underneath all of it. Betelgeuse is roughly 700 light years away. The light reaching your eyes when you look at it tonight left the star around the year 1325. That was before the Black Death reached Europe, before Gutenberg, before Columbus. Whatever has happened to Betelgeuse in the 7 centuries since that light departed, we have no access to. If the core collapsed last year, the neutrino burst is already en route. The light from the explosion is already en route. We don't know. We can't know. The detectors are ready. The trigger files are loaded. But the star itself is keeping its own timeline, indifferent to ours. What the scientists monitoring Betelgeuse are doing, in the most literal sense, is watching the closing chapter of a 10 million year story. They may not see the ending. The ending may not come for 100,000 years, or it may come before the next issue of whatever journal they publish in. That range is not a failure of science. It is an honest accounting of what observation can and cannot reach. We can study the surface, we can track the atmosphere, we can measure the light in ultraviolet wavelengths and map the wake of a companion star moving through gas that stretches across millions of kilometers. And we still cannot tell you when it ends. That orange-red point of light in Orion's shoulder is 700-year-old light from a star that dwarfs everything in our solar system. Its surface, if it replaced the Sun, would extend. Its convection cells are lit. It is losing mass at a rate 30 million times higher than the Sun. Already shrugged off the outer layer of its southern hemisphere in a single violent event in 2019 and recovered and kept burning. Or it may not have fully recovered. Scientists are still looking at the data. Every generation that ever watched Betelgeuse looked at a star they assumed would always be there. We are the first generation that knows it won't be. We know what it is. We know what phase of its life it's in. We know what comes after carbon burning, and after neon burning, and after oxygen and silicon. We know what iron does to a stellar core. We know what a Type II supernova produces, and how the neutrinos will arrive before the light, and what the expanding nebula will eventually look like. We have built instruments specifically to catch the moment it happens. The star does not know it is being watched, but we are watching, and whatever happens next, whether it burns for 100,000 years, or whether the neutrino detectors trigger tonight, we are the first generation in human history that would actually understand what we were seeing.